Now we want to talk about the topics about the rate of change. So we know that the difference quotient, which is given by f of x plus delta x minus f of x divided by x plus delta x minus x, which is equal to f of x plus delta x minus f of x over delta x. So this is the difference quotient. The numerator is the change in the f values or y values. The denominator is the change in the x values. It tells you the rate of the y values change based on the x value change, right? So we denote this one by the delta f, which is the change in f based on the change in x. We use this notation to denote this difference quotient. We give a name, which is called average rate of change. Okay. And we also know if we take the limit that delta x approaches 0 of f of delta f over difference quotient of delta x, which is equal to the limit delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And this limit gives you the derivative of f at x. So we give a name, which is called instantaneous rate of change. Sometimes we just call it rate of change. Okay, so while it's called instantaneous rate of change or rate of change using this limit, let's look at an example for the rate of change, which is the velocity in physics. This is a very good example. So we consider a moving object on a straight line. So we let s of t be the position function of this moving object. That means at time t, where is this object? Suppose we have the object at time t sub 0 is here. Then after some time period, at time t, it would be here. So this is the position at time t naught, and this is the position at time t. So if the moving object from this point to this point, what is the velocity? The velocity we know, which is the distance traveled, which is s of t minus s of t naught divided by t minus t naught. This is the distance traveled divided by the time period from t naught to t. So the time for the traveling is t minus t naught. So this is the distance divided by the time, which is actually the delta s over delta t, right? The change in the position over the change in time. So this one will give you the velocity, right? So actually this is the average rate of change. Rate of change. It's actually the velocity we have learned in the physics, which is actually the average velocity. Average velocity. So the average rate of change for the position function is actually the average velocity. Okay, so many problems we solved in high school to find the velocity. The velocity means the average velocity. So if this time t is very close to the t naught, then the average velocity will approach. So if t is very close to t naught, okay, this is t naught, this is t is very close to t naught. So the average velocity will approach the velocity at the t naught moment, at t sub 0. Okay, so this will give you the limit t approaches t naught of s of t minus s of t naught and the t minus t naught. What's that? This is the s prime, the derivative of this function s at t naught. This is the another definition for the derivative, right? And this one is actually, as I said, if t approaches t naught, the average velocity will approach the instantaneous velocity at this moment t naught. So this is called the instantaneous velocity. At t naught, which is denoted by v at t naught. So now this is actually the rate of change, right? The instantaneous rate of change. So the rate of change of the velocity is actually gives you the instantaneous, the rate of change of the position function will give you the instantaneous velocity at this moment. Okay, so in the future, we are really interested in the instantaneous velocity, not the average velocity, right? So now let's look at the next example. So now let's look at the example that we release a ball from the top of a high enough tower. We want to find the instantaneous velocity of this ball at the moment t equals 0.8 second. So we are given, so this is the graph, okay. At different moment, you see the ball has a different velocity. We want to know what is the velocity at t equals 0.8 second. So we know the position function is given, which is 4.9 times t squared. So now we know the velocity, the instantaneous velocity is actually the rate of change of the position function, which is the derivative of s, right? The position function. So this is the derivative. And the derivative, so here prime, s prime, prime means take the derivative about t. So it's actually the variable is t, not x anymore, right? So we plug in 4.9 t squared, take the derivative, then we use the scalar multiplication rule. You will get, we bring out 4.9, so you get 4.9 times t squared, take the derivative. Then we use the power rule, right? We bring down t to 2, then subtract 1 to get a new power. So at last you will have 0.98 t, 9.8 t, right? So this is the instantaneous velocity at any time t, right? So we care about, the problem care about at the moment t equals 0.8. So we plug in 0.8. So we evaluate t at 0.8. Then you plug in, you will have 7.84. This would be your result.